Good day, everyone. Welcome to the second session on PAMI, an open source Python framework to discover interesting patterns in big data. In the first session, we have covered three parts of this tutorial, in which the first part introduced you to the field of pattern mining. In the second part, we have discussed what is a PAMI software, how to install it, how to manage it, and if you have any bugs to report, where to report them. In the third part, we have discussed how to create different types of data sets that can be used in our PAMI software. In the final part, that is part 4, we will look at the demos of our PAMI software. So the first one is we will discuss how to get the statistics of a database. Means how the item frequencies are, how many number of transactions exist in the database, and many other statistical details. Next, we'll look at how to implement pattern mining algorithms using PAM. Finally, we look at how pattern mining or PAMI software can be integrated into existing ML packages to find useful knowledge. So this part may find very interesting to the users, and it opens a new way for upcoming researchers to publish top quality work. So now let's look at getting the database statistics. To get the statistics of a database, we have to import a package that is available at pami.extras.dbstats. So we have to import this program to get the statistics of a transactional database, temporal database, and a utility database. So this is the library that we have to use. So let us look at the live demo in which we show how to print the statistics of a database. So we have already created a Jupyter file. So let's do it. So first, I am taking a file. So I'm defining a variable which uses the file from the internet. So I have kept the file as a HTML link that can be downloadable. So you can also specify a data frame also, it will work. So I am taking the file. Once I have taken the file, next we have to import the module. So please import the module using import pami.extras.dbstats. Because this is a transactional database, we have to load the library or program transactional database stats as TDS. So we are now importing this necessary module. Next, to this module, we pass the file. And then we run the program. Once we run, then we can ask different parameters. So we can get the database size, number of items in the database, then what is the sparsity of the database. You can see that the database sparsity is 0.88. Means most of the items have 0 values in the data set. Next, what is the minimum transaction size average transaction size, maximum transaction size, then the standard deviation of the transaction length, and the variance of the transaction length. So such kind of statistical information can be generated for a data. These statistical details are crucial in choosing the algorithm because the transaction lengths and the item frequencies impact the performance of a algorithm. For example, if a data set has very small has a very small number of transactions, then a priori kind of algorithms are better. If a data set has very long transactions, then pattern growth algorithms are better. So these characteristics will help us in choosing the algorithm or in understanding why a particular algorithm is better over other algorithms. Afterwards, sometimes what we need to do is we need to store the distributions so of the item frequencies and the transaction length. In that case, what we have is we have some additional functions. So if you want to print the item frequencies, we can simply say item frequency is equal to obj dot get sorted list of item frequencies. So this will give us a file, a list with item and its frequencies. We can store this list in a file for future purposes. Similarly, we can store the distribution of item frequencies. Here as shown here. Sometimes what happens is we want to see the results of how the distributions are. To see the distribution graphs, then please import pami.extras.graphs dot plot line graphs from dictionary. So you can input any dictionary to this algorithm and it will print the graph. So what I am trying to do is I want to see the item frequencies. So if I specify here 100, okay, so I'm saying plot item frequencies 100% means print all the items in this list. Okay, so this is the title. Title is item frequencies. The X label is item rank. The Y label is frequency. You can see here we are printing the value. So if we specify 100%, then this is the graph by which we can see. If we want to see only 50% of the items in the item frequencies, then we simply specify 50%. We execute. Then we can see only the 50% of the items. Why 50% of the items is sometimes there will be many items because the real world data sets follow long tail distribution. Many times the tail items will have very less frequencies. They may not be of interest to the user. So in such cases, by choosing top K frequent items to print, we can understand how the distribution is. Similarly, we can look at the distribution of transaction lengths, how the transactions are being distributed in the dataset. You can see that most transactions are having the length of 10. So such kind of information can be found. And similarly, very few transactions are having very very large number of items. Such kind of crucial database statistics can be discovered from this database statistics package. So having understood the database statistics package, now what we try to do is we want to mine the algorithm. So to mine the algorithm, or that is implementing the algorithm, we have three demos. One is how to use, the first one is demo 4 is how to use the basic algorithm. Next one is how to use the algorithm by varying the threshold values. And the last one is how to execute the algorithm by varying the threshold, threshold values and different algorithms. So let us look at these demos. So as the title suggests, in demo 4, what we are trying to do is we are trying to find frequent patterns using FP growth algorithm, which is a well-known pattern growth algorithm. So how do we do that? First, we specify the database. Next, we specify the minimum support threshold value. So we have specified the input parameters. Now what we have to do is we have to execute the FP growth algorithm. So to execute the FP growth algorithm, first we have to import it. So from PAMI dot frequent pattern dot basic import FP growth. So this is the algorithm FP growth as EP. So I am importing this algorithm. Once I have imported this algorithm, I will now execute this algorithm. So what is the methodology to execute this algorithm is obj equivalent to EP, that is FP growth dot FP growth database, that is the file, followed by minimum support parameter. So with this step, I am initializing the algorithm. Next, after initialization, we mine. So we mine the algorithm. We start the mining process. This process will find all frequent patterns that exist in the database. Once we have identified all the frequent patterns, what we can do is we can store these patterns as a file. So I am saving the patterns in a file. Similarly, I am reading the patterns as a data frame. So if I want to use the patterns in some other task, like in visualization, I can read the patterns as a data frame. And also if I want to know the total time, the runtime taken and the memory, we can also print them here. So if we want to print the, sorry, we have to run the entire algorithm. Otherwise it will not work because the object obj was not initialized. So let's, so you can see I have initialized DB, then minimum support, then FP growth has started. So we have now mined the patterns and we are now saving the patterns in a file patterns.txt. After saving, we are also reading the generated patterns as a data frame, and we are going to print the memory and runtime requirements of it. So this is how the basic one. So if you want to find the patterns, you can simply see. So this is the pattern and this is the support. So we have a total of 13,254 patterns have been discovered from this dataset, T10 I4 D100K dataset. So this is how we will be implementing the algorithms in PAMI. We now discuss how to mine the patterns using the FP growth algorithm in PAMI. So first, let us specify the data set. So let us say this is the database. So after specifying the database, now what we do is let us specify the minimum support. So let us specify minimum support as 100 in count. So now we have specified the database. Now let us use the algorithm, frequent pattern mining algorithm. So for that purpose, we say from PAMI. So we want to look at frequent pattern. So let us look at basic. So we are looking at the basic algorithms. So in the basic algorithm, we have a priori, eclat, bit set, eclat diff set, and FP growth. We will try FP growth algorithm as alg. So we are importing the algorithm. Now what we will do is, we will call the algorithm. So we can see that input is a file, minimum support, and the separator. So what we try to do is input is the database. So I file equal to database. Minimum support is equivalent to minimum support. In our case, it is 100. And then separator. So if you are, in our case, our separator is same as backslash tab separator. So now we have specified. Now let us start the mining process. So obj dot start mine. So this will start the mining process. So the mining process has started, and then the pattern mining step will happen. Once this step completes, now what we can do is we can store the pattern. So to store the patterns, let us say obj dot save patterns. So this is the function. So in this function, we have to specify the file name. So to specify the file name, we have to provide the, so let us say the pattern is frequent patterns. Minimum support is 100. Dot. So this way, we can save the patterns. You can see that the file has created. If we want to read the patterns as a data frame, we can say frequent patterns data frame equal to obj dot get patterns as data frame. So this function will output all the patterns into a data frame. Once this is done, we can even print the data frame using this command. And if you want to print the runtime, we can also print the runtime. Obj dot get runtime will print the runtime results of the algorithm. So as you can see, there are 27,532 frequent patterns that have generated. Now, if we want to know the runtime results, we can calculate the runtime. So it took 11 milliseconds for the completion. If we want to calculate the memory, we can also print memory. So we have both RSS memory and USS memory. So RSS memory. So this is the total amount of memory the algorithm took in terms of byte. So this way we can extract the patterns from the database. Now, in this case, we have simply used one minimum support. Sometimes if we are a researcher, we want to evaluate the performance of FP growth algorithm by varying different minimum support values. For this case, what we do is the algorithm is almost simple. So what we do is first we specify the file name, then we choose the list of minimum supports, means the minimum support values that I will be using to evaluate the FP growth algorithm. Once I have specified the minimum support values, I will import the FP growth algorithm from the PAMI library. Next, I will also initialize the runtime, patterns, and memory parameters. So these lists will store the values at different minimum support lengths. Next, the process is very simple. For each minimum support list, we simply call the FP growth algorithm, and then what we do is in this runtime list, we store the runtime. In the patterns list, we store the total number of patterns that are getting generated. Next, in the memory list, we store the memory value. So at different values, whatever we get, we simply store them in the list format. Once we store them, what we do is we simply use the graph package in the PAMI to print the graphs. So what we do is, it's a very simple process. From PAMI.extras.graph import plot line graph from dictionary as PLT. So we import this library and then we simply draw the graph. So patterns, 100% print all the patterns, title, minimum support, labels. So once we do this plot function, we get the graph. So we can see how FP growth is varying by changing the minimum support. For example, as we increase the minimum support, the number of frequent patterns that are getting generated are falling down. This proves that increase in minimum support has negative effect on the generation of patterns. Since the number of patterns are getting reduced with the increase in minimum support, the runtime and memory is also getting reduced. Means minimum support has negative effect on runtime and memory requirements. Especially if you see the runtime graph, not in a uniform manner, but there is a linear decrease in the memory requirements of FP growth algorithm by varying minimum support. So this kind of information can be generated using PAMI. Next one is we want to evaluate several algorithms. So if we want to evaluate different algorithms, what we do is very simple. This extends the previous one. First, we have to create. So in this case, what we are doing is we are evaluating several frequent pattern mining algorithms, that is a priori, FP, growth, eclat, or eclat on the data sets. So the task is very simple. First, we have to create an empty data frame to store the results of algorithms, minimum support, patterns, runtime, and memory. So this is the first step. So we have created a data frame. Next, what we have to do is we have to specify the data set. I have specified the data set. Similarly, I have also specified the minimum support values as a list. Next, I am choosing the algorithm. We have to import the algorithm, execute the algorithm, and store the result in the data frame. So this is the important step that we have to do. So I am specifying a variable, that is algorithm is equal to a priori. So this is the algorithm. Using this algorithm, I am going to generate frequent pattern. So from PAMI dot frequent pattern dot basic, import a priori as algorithm. So we have imported the algorithm. Next, for each minimum support in the minimum support list, what we do is we pass the parameters. So we are now calling the a priori algorithm with dataset minimum support, and then we have started the mining process. Once the mining process has been completed, what we do is the results that we get for this are stored in a temporary data frame using algorithm name, the minimum support used, number of patterns, runtime, memory. So in this way, the results are being stored. So this data frame will be appended to our result data frame. So once we append these results, next what we do is we change the algorithm. Okay, so now from a priori we have moved to FP growth. For FP growth also the same thing. Import the algorithm at different minimum support values, execute the algorithm, and store these temporary results into a data frame and append. The same was done for another algorithm, eclat. Okay, so the idea is very simple. Execute the algorithm and push those results into the data frame. Once we have the results, next what we do is we simply use plotly to generate values. So we say import plotly dot express as px. So here we are drawing the plots. So these plots will be now used to see the results. Which algorithm is performing better, which algorithm is not performing. You can see that a priori algorithm is taking much runtime than the remaining FP growth and eclat algorithms. Similarly, memory also, if we observe, a priori is taking less memory over FP growth and eclat algorithm. So such kind of information can be generated using the PAMI software. We now discuss how to use PAMI along with machine learning packages. So Here is the real world application of our software. So we call it air pollution analytics. So the government in Japan has set up a sensor network to monitor pollution throughout the Japan. The spatial location of the sensors is shown in the figure A. This sensor network collects data for various pollutants, say PM 2.5, at hourly intervals. This data can be transformed into a temporal database as shown in figure C. On this temporal database, we can apply frequent pattern mining and other pattern mining techniques to identify the locations in which people were exposed to high levels of air pollution. So this is the overall picture of the analytics, air pollution analytics. We will now show you how we can do such analytics using PAMI. So coming to this, so this is the air pollution data set of PM 2.5 taken from on 1st of January 2020 to 29th of February 2020. So PM 25 2020. So you can see that each line represents a transaction, and this transaction and the item is the point, the spatial information of the point. So each point represents an item, or in our case, it represents a sensor ID. So the first transaction says that the following points have recorded high levels of PM 2.5 at 00 hours. Similarly, the second transaction represents the sensor IDs that have collected high levels of PM 2.5 at 1 hours, and so on. So we have this information, which is similar to the temporal data set. Once we have this temporal data set, we will apply the frequent pattern mining algorithm. In our case, we use a variant of frequent pattern mining algorithm called frequent spatial pattern mining algorithm to identify the locations at which high levels of pollution was frequently observed. So how do we do this? So here is our demo. So here we are specifying the data set, and then we call the algorithm FSP growth. And then we are specifying distance parameter called maximum distance. Means if we are finding a pattern, then all the sensors or items within a pattern should not be more than 5 kilometers. So that was the condition we have applied. And then we have specified the minimum support of 400. And this is the distance function which we use to identify the neighbors. So in this step, first what we do is we apply Euclidean distance function on the data set. So this is the data set. So we have taken air pollution data set. On this data set, we are applying Euclidean distance to identify a neighborhood file. Means for each sensor, we try to identify the points which are neighbors to each other. So once we identify the neighbors, then what we try to do is we try to call the function called FSP growth algorithm. So this algorithm will take the data set as an input, the neighborhood information, and the minimum support threshold value. Once we specify the input parameters, we simply say start mine. So this function will do the mining process. Once this is done, what we do is we take some final patterns and then we plot them on the map. So to plot them on the map, we simply use PAMI extras plot point on map. So we use this function to plot and then we get the results. So let's run the code. So we are first importing the programs. Now we are generating the neighborhood file. So for each sensor, we are identifying the neighbors. So this will take some time because there are several items, and for each item, we identify its neighbors. Once we identified the neighbors here, we now perform frequent spatial pattern growth algorithm using the dataset and the neighborhood information. So once we complete this process, what we will do is we take the patterns and we will plot them here. So let's wait for some time and we will get the result as the graph. So as you can see here, so you can see that these are the locations where high levels of PM 2.5 was frequently observed during the first 2 months of 2020. So even though in 2020 we had COVID and lockdowns, still we can see that there are some significant activities that have gone through the places in Tokyo. These are the places. This is the central Tokyo. Tokyo. So here we can see that people who are very close to the sensors are exposed to high levels of PM 2.5. Similarly here in Tokyo area. Similarly, if you go to south of Japan, we can observe that there are some locations where heavy pollutions was observed. So such kind of information can be found extremely useful for the users or the environmentalists in coming up with the policies to control emissions. So this is one of the advantage of our model. In our model, we have used the existing data to identify the locations. What others can do is they can take the recordings of pollutions and then make the prediction of the air pollutions. Once we make the predictions, we can convert the predicted data into a transactional or a temporal database, and we can extract the patterns from the air pollution data. So they represent futuristic patterns. In our case, they represent historic patterns. So such kind of futuristic and historic patterns can be discovered using our PAMI library. So this is one approach by which we can do. Now coming back, so we have discussed air pollution analytics. Now we will discuss another interesting application of how machine learning can be used along with PAMI to discover knowledge hidden in the data. So here, assume we have some image data set. So this image data set, when provided to instance segmentation algorithm, what this algorithm will do is for each image, it identifies objects and their probability. For example, in this figure, there is a car with 0.4% probability. There is a person with 0.3%, 0.3 probability, and there is a bus with 0.1 probability. So the instance segmentation algorithms identify objects and their probabilities. This information is called as futures database because they are the futures that are available that were identified in an image. We call it futures database. This database can be converted into an uncertain database by specifying a threshold value. For example, if we specify that the probability of an object must be more than 0.2, then we can simply say that this futures database can be converted to uncertain database with car 0.4, person 0.3. The bus probability is 0.1, which is less than our threshold value. So we don't consider it in the generation of uncertain database. So what we do is we create this uncertain database. Once we have this uncertain database, we simply input this data set to the uncertain frequent pattern mining algorithm that is available in our PAMI library. And this program will identify the frequent objects that are appearing together in our data set. So let us look at this demo. So let's go to BDA part 2. So in this data set, what we have is we have images of cats and dogs, several of them. You can see there are several cats and dogs images. So using this data set, we try to identify the objects. So for object identification, we have written the Python program called object detection.py. This algorithm basically uses ResNet to identify various objects and their probabilities in the image dataset. So this is the algorithm for identifying the objects. Okay. So this program will identify the objects, and these objects we will be using. So let us look at how we can use image segmentation techniques and the algorithms in PAMI to discover useful information. So in the first step, we import all the necessary libraries that are needed for KDD purpose. Next, we mention the path of the images. Then the output, that is the database file in which we are going to store the futures, will be chosen as an input parameter, that is output file. Next, what we do is for each file in the image directory, okay, so for each file in the image directory, we open the file, and then we try to detect objects. So first one is model predict. So we try to train the model, and then once we train the model, we try to detect the objects from the test data set. So since the model is already trained, we simply pass the image data set to identify objects. So once we identify the objects, okay, we get this futures database. The futures database is converted into an items dictionary using the threshold value. In our case, we prune all the objects whose property is less than 0.8. Once we have it, we simply store the values. So this will generate us an uncertain database. This database will be passed to uncertain frequent pattern mining algorithm to discover useful frequent patterns. So first one is here we are creating the uncertain database. Now what we are going to do is we are calling PAMI dot uncertain frequent pattern dot basic. So in this algorithm, in this library, we have the algorithm called puff growth algorithm. So using this algorithm, we try to extract the patterns and then store them in the database. And then we run it. So this is the purpose. Until now, we have given the demos on how to use the algorithms in PAMI to discover hidden patterns in big data. We now conclude our tutorial with the following conclusions. The first, we have introduced you to the PAMI library. Then we discuss the methodology to create different types of databases. Next, we explained how to mine patterns using pattern mining algorithms. And finally, we have presented the real world applications of our library. We now end our tutorial and we are now open to questions. Please feel free to ask your questions. Thank you very much.